Welcome to Unit 7 of Chemistry 101 online at Goodwin College. Unit 7 covers Chapter 7, so we're skipping Chapter 6 for this week, and we will come back to it at a later point in time. But right now, in my opinion, Chapter 7 follows a little bit better after Chapter 5. So that's what we're going to do this week. Chapter 7 deals with solutions. Some of you may already know what a solution is. But for those of you who don't, I will give a definition, and the definition is here. I'm circling it. A solution is usually a liquid. It doesn't have to be a liquid. It can be a gas as well. But if it helps, you can think of it as being a liquid. Solution is usually a liquid where one or more things, and I'm putting things in quotes there, are dissolved in something else. There are formal terms for the things that are dissolved. The things that are dissolved in a solution are called solutes. And there's the word there, and you'll need to know that. The things that do the dissolving, the liquid or the gas that does the dissolving, is called the solvent. And again, you should know that. And the two together, the solute and the solvent together, make something called the solution. So again, solvent is the thing that does the dissolving in a solution. The solute or solutes are the things that are actually dissolved. So if I told you that I had salt water from the ocean, again, you can pause the video at this point and think about the answers to these questions. But if I told you you had salt water from the ocean, and I said, what is the solute and what is the solvent, you can pause here and think about this. This may be sort of clear to many of you already. The answer is that the salt that's dissolved in the salt water is the solute, and the water itself, just pure water, is the solvent. But salt water altogether is a solution that contains salt and water. So at this point I want to talk about one particular type of solution, and that is salt water. So dissolving sodium chloride, NaCl, is the chemical formula for table salt. I'm pretty sure that many, if not all of us, have dissolved table salt in water. You usually do this when you're making pasta. When you're boiling the pasta, you might throw some salt in, and the table salt dissolves in the water. So many, if not all of us, have made salt water solutions. When you dissolve table salt in water, the following takes place, and this is a little bit different chemical equation than you're accustomed to seeing, but most of it should be familiar with you. Here I'm saying that I start with solid, that's what the parentheses S here means, solid table salt. I mix it with water, and here the formula for water is above the arrow, don't worry about that. But basically I'm taking solid table salt, mixing it with water, and what I'm telling you is that once the solid table salt has mixed with water, the things that make up the table salt break apart into their component ions. So if you remember from very early in this course, I told you that sodium atoms prefer to have a positive electrical charge, a charge of +1, and that chlorine atoms prefer to have a negative electrical charge, a charge of -1 for chlorine. And because they have opposite electrical charges, they are attracted to each other, and they stick to each other, and they make solid table salt. And what I'm saying is that if you take solid table salt, mix it with water, the ions actually disconnect. They break apart so that the sodium is floating around, the sodium ion is floating around in the water more or less all by itself, independent of the chlorine ion. And the chlorine ion is basically doing the same thing. You can think of it as floating around inside of the water more or less all by itself. Now, I tend to show this to my students in the on-ground course, and then I tell them this. Basically, I ask them, do you believe this? And pretty much everyone says yes. They say, yes, we believe this. And then I say, what if I'm lying to you? What if it turns out that you take solid table salt, you mix it with water, and the ions don't actually disconnect? Once the table salt dissolves in water, like it might if you were making pasta and threw some salt into the pan of water, maybe the ions don't disconnect at all. These ions are still stuck to each other just like they were with the powdered table salt. And it's just that they are stuck to each other like that, and they're dissolved in the water that way. And basically what I ask the students is, I say, how do you know that the top situation is true as opposed to the bottom situation. And at that point, many of the students begin to question whether the top situation is actually a lie and whether the bottom situation is actually the truth. And for most of you, you can't really tell. For the amount of information that you know about chemistry, you don't necessarily know yet whether the top situation here is true or whether the bottom situation here is true. Now, I will tell you, the reality is the top situation. The top situation is actually true. The question that I then ask my students on ground is, how can you actually tell that the top situation is true and the bottom situation is not true? And for those of you who've read Chapter 7 or have sort of seen this before, you know the answer to that. The answer to that is that if you mix solid table salt with water, the ions actually disconnect. And the way that you can tell is that the ions conduct electricity. If you take a specially made light bulb, and I'll point you to a video of one in a minute, but basically if you take a specially made light bulb where the electrodes of the light bulb, here's one electrode and here's another electrode, are inserted into water that contains table salt dissolved in it, the ions in the table salt, because they are disconnected, they can actually capture electrons and travel from one electrode to the other, and they end up turning the light bulb on. If that wasn't true, if you dissolved table salt in water and the ions remained connected to each other, in other words, if they remained connected to each other and neutralized each other, then these molecules here would not be able to capture electrons and basically carry them from one wire to the other, and the light bulb would not turn on. It turns out if you have a specially made light bulb, and again I'll point you to a video of one in a minute, if you have one of these specially made light bulbs and dip it in salt water, the light bulb actually turns on, and it turns on pretty brightly as long as you have enough table salt dissolved in there. And this does not happen. So that's sort of the experimental evidence for the fact that table salt, the ions in table salt will disconnect from each other and float around more or less freely in water when you dissolve it in water. These ions, because they can carry electrons or can interact with the electrons coming off of this wire and conduct electricity, those ions are called electrolytes. So many of you may have heard the term electrolytes before, and basically it's a chemistry term that is trying to tell you that you have ions in a solution that are capable of conducting electricity, which is why they're called electrolytes. So as far as the video is concerned, I'll show you that on the next slide. So at this point I am going to show you a YouTube video that just basically showing you what this actually looks like. And don't get too caught up in the details of what the narrator is talking about. I will try to explain in my own words in the next few slides after the video.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity. I will put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve the material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add just a little bit to the water and stir it up. As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte.
So unfortunately, only the on-ground students actually do this type of lab. It's an interesting lab where you get to see sort of this light bulb turn on in a similar way as you saw in the video. But at least you can get an appreciation of it from watching the video. So the narrator in the previous video was calling table salt a strong electrolyte. There are things called weak electrolytes as well, and let me basically try to explain it in this way. In the situation with table salt, if you dissolve solid table salt where the ions are connected to each other in the solid, if you dissolve that solid into water, virtually all of the ions in table salt disconnect from each other, and virtually all of them are floating around more or less independently of each other. Because of that, there are a lot of ions floating around in the water, and because of that, you can think of the light bulb turning on strongly. And because of that, table salt is called a strong electrolyte, at least when it's dissolved in water. You could imagine a situation where you dissolve the table salt, and some of the table salt molecules still remain stuck to each other. Some of the ions in the table salt molecules remain stuck to each other, whereas some of them actually disconnected and floated around freely. There could have been a situation like this. It turns out that with table salt dissolved in water, it is like the situation on the left. But if it was the situation over here in the middle, then if only some of the ions are breaking apart and disconnecting from each other, maybe the light bulb would turn on weakly. And because of that, there are molecules that behave this way, that only have their ions disconnect some of the time. Those types of molecules are called weak electrolytes. And I'll show you an example of that in a few minutes. There could have been a situation like this as well, and this I posed to you as a hypothetical at the beginning of this section, where I said maybe if you dissolve table salt, the ions don't disconnect from each other at all. They still dissolve in the water, but they're not disconnected. If that was the case, and I am telling you that for table salt it is not the case, but if that was the case, then the light bulb would not turn on at all, and you would have said that this material here is a non-electrolyte. So there are basically different ways of categorizing electrolytes, or molecules, let's say. There are molecules that don't break apart into ions at all. They're non-electrolytes. There are molecules that might break apart into ions a little bit. They are weak electrolytes. And then there are molecules that break apart pretty much completely into component ions, and those are called strong electrolytes. So I'd like you to know the difference between all of those in those general terms. And then this is an example of a weak electrolyte. This is the formula, CH3COOH. I believe I showed this to you in the previous unit when we were practicing understanding molecular formulas. This is the formula for acetic acid, which is actually the main ingredient in vinegar. If you take acetic acid, mix it with water, the H here, the hydrogen atom here, will actually sort of break away from the rest of the molecule, and it will break away as an H plus ion, and the rest of this molecule will be negatively charged. However, in the case of acetic acid, when it's dissolved in water, it only does this. It only breaks apart into these ions a little bit. Some of the time, the molecule actually stays intact like this. So if you could imagine a situation where you had acetic acid dissolved in water and you could zoom in and look at the molecules, some of the molecules would remain intact, some of them would be broken apart. And because of that, if you had equal amounts of table salt over here and acetic acid over here dissolved in water, the table salt light bulb would turn on very brightly, the acetic acid light bulb would turn on much more dimly. And because of that, you can actually tell that acetic acid is a weak electrolyte. There are examples of non-electrolytes as well. The easiest example to understand is this molecule here, which is glucose, which is a sugar. I'm sure everyone here has dissolved sugar in water, or at least sugar in coffee, or something like that. If you take sugars, many sugars, like glucose, like sucrose, and we haven't talked about sucrose yet, but there are many sugars that will dissolve in water. And if you dissolve them in water, for the most part, these sugars are not made of ions at all. They're actually made by, the atoms are attached to each other by covalent bonds instead of ionic bonds. So this molecule of sugar here does not actually have any ions at all. It will dissolve in water, and you can see it shown here. The parentheses AQ means that this sugar molecule is now dissolved in water. However, because this thing is not made of ions, when this sugar is dissolved in water, it will not conduct electricity. So if you had an equal amount of sugar dissolved in water and you performed this little light bulb experiment that you were seeing in the video, the light bulb would not turn on at all. And because of that, you would say that glucose, or this particular sugar over here, is a non-electrolyte when it's dissolved in water. So, as far as electrolytes are concerned, what I want you to realize is that some materials will dissolve in a liquid, and the ions, if it's made of ions, the ions will disconnect from each other. The molecule will basically break apart into ions that act independently of each other. These types of materials are called electrolytes. Some materials won't break apart into ions at all. One example of this was glucose on the previous slide, a type of sugar. Those are called non-electrolytes. Some materials only break apart into ions a little bit, like the acetic acid that I showed you 2 slides back. Those are called weak electrolytes. And one thing to point out here that may not be obvious is that I am basically telling you that table salt breaks apart into ions very well when it's dissolved in water. One thing that you may think I'm glossing over, but I'm not actually, is that I keep saying when it's dissolved in water. That's table salt is a strong electrolyte when it's dissolved in water. You can actually dissolve it in other liquids where the ions in table salt don't break apart. And if they don't break apart, then you would say table salt is a non-electrolyte when it's dissolved in some other liquid. And so the punchline here is the degree to which a compound breaks apart into ions actually depends both on the compound that you're dissolving and on the solvent, on the thing that's doing the dissolving. In the case of water, table salt dissolved in water makes a strong electrolyte. In the case of acetic acid dissolved in water makes a weak electrolyte. But that's not necessarily true when you dissolve those things in other types of liquids. So that's the end of the introduction to electrolytes. The next section is going to deal with something called solubility.